Good afternoon, everyone. We are Sara and Ignacio from Concordia team, and we'd like to present to you our purpose for the challenge, magnetic reconnections. We are both students of aerospace engineering in the University of León. And yeah. Well, magnetic reconnection, or MR, is a phenomenon caused when the z coordinate of the interplanetary magnetic field and the z coordinate of the Earth magnetic field go in the same direction with the opposite sign and come together, releasing a big amount of energy, so that a big hole is created in the magnetosphere so plasma can penetrate. This causes two types of effects: atmospheric ones and space ones. In the atmosphere, they cause atmospheric and meteorological phenomena such as auroras and the interruption of power generation and transport. And on the other hand, we've got damage to satellites that causes a big impact on our communications and GPS signals, so that our society and financial stability is affected too. And as we have said, satellites are damaged in two different ways. In the first place, their physical integrity, as you can see. Photoelectric effect combined with radiation causes a phenomena called surface charging, which as a consequence causes degradation of electronic components and the necessity to recalculate the orbit. And on the other hand, we've got a damage to the signals, which are in some way rotate its polarization, refract it, or even experiment amplitude or phase variation.
So knowing now the effect and impact of the MR in our society, we approach the challenge with the OmniWeb NASA web and the data of the 3 satellites that affect the solar plasma studies. We had one first hypothesis about the Z component of the vector, but we had to discard that because we didn't know if our satellite was located in the MR point. So the Z component would not be the same as the MR point. So what we thought is that the MR is detected through disruptions on the magnetosphere, because when energy is released, kinetic energy and heat from plasma gets into the sensors of our satellite. And we plugged those data into our studio and made a big magnitude graph that also connects with the solar cycle of 11 years graph. And we actually could see that the peaks of magnitude of the IMF detected by our satellites agree with the peaks of the solar cycle. The minimums around 2008 accord as well, and then they rise again for the second solar cycle. That can be seen as well in the plasma temperature detected by our sensors. They both agree with the sunspots that have been detected in the solar cycle. Again, the rise in the early 2000s to the drop to the minimums of the 2008, 2009, and rises again for another cycle of 11 years. And then we tried some seasonal approach for it to see if we could see that there's more activity of MR during summer or winter, but we didn't find any substantial relation to the sunspots that were detected, more than some peaks during March. We can see them that could be related with the Aurora Borealis season that is also in March. And what we would have liked to do with more time and resources is to create a program that worked with an AI to further analyze and predict these patterns in MR to see if that can help us with future safety of our satellites. So this is our radiography, and this is all. Thank you very much for your attention, and we're happy to answer any questions.